Today in Math 30-1, we're taking the last topic in Chapter 1, and that is the inverse of a relation, topic 1.4. The inverse of a relation can be found by interchanging the values of x and y in each ordered pair. And what that means is every point on our graph xy is going to become reversed yx. This means the graph will be a reflection of each other in the line y equals x. We're going to look at that in example 1. The inverse of a function, y equals f at x, may be written in the form of x is equal to f of y when the inverse of a function is itself a function. It is going to be written as f inverse of x. That's not f to the power negative 1 of x, that's f inverse of x. When the inverse of a function is not a function, it may be possible to restrict the domain of the function to make it a function, to make the inverse a function. We're going to look at that in example 2. Lastly, we can determine the equation of an inverse function by interchanging x and y and then solving for y. And we're going to look at doing that in example 3. In example 1, we're asked to graph the inverse, state the domain and range of a relation and its inverse, and then determine if the inverse is a function. So here we go. We have these 3 points connected on our graph. The point negative 3, 0, negative 2, 2, and negative 1, 0. Those are the points on our relation. That means if I plotted the points for my inverse, we're going to write 0, negative 3, 2, negative 2, and 0, negative 1. Now if I plot those points, 0, negative 3, that's going to be those dots that are joined in red. The line in blue is simply the line of y equals x. That's going to be the line that it's going to be a reflection over. Secondly, is this a function? Well, it won't pass the pencil test if you remember that if you drew a line anywhere across it, that means that it'll cut across the function in 2 different places. That means it's not going to be a function. The domain is 1, negative 1, negative 2, and 3, and the range of our function is 0 and 2. Notice that in the inverse, the domain is now 0 and 2, and the range is now negative 1, negative 2, and 3. So noticing this, the inverse is not a function, and that means also that the domain of the original function is going to be equal to the range of the inverse, and vice versa. The range of the original function is going to be the domain of the inverse. That's what makes it an inverse function. In example 2, we're going to graph f at x equals x squared minus 2 and its inverse, and we're going to ask, is the inverse a function? And then, how can you restrict the domain to make it a function? Here we are, plotting 5 points. We've got the points when x is 0, y is negative 2. When x is 1, y will be negative 1. And when x is 2, y is going to equal positive 2. And when x is negative 1, it's going to equal negative 1. And when x is negative 2, our function is going to be equal to positive 2. So there is the graph of our original function. Now, if I drew the inverse and wrote the points backwards, instead of the point x is 0, y is negative 2, we're going to go negative 2 and 0. That's the red dot on our graph. Next, we're going to plot those other points the same way, and when I graph it, now I can see that that's the graph of my inverse function. If I draw in there the blue line, which is the y is equal to x line, we can now see that the inverse is not a function because it won't pass the vertical line test. But if I restrict the domain of my function to only x being greater than or equal to 0, then I can make the inverse to be a function as well. In other words, instead of having the whole graph, I'm going to take away just the part that's negative. So then I only have the positive half of the graph. If I just have the positive half of the graph in red, in black, I take the inverse, that's going to be the positive half of my graph in red, and now I have the inverse also being a function. So here we are at example 3. Determine the equation of an inverse. Well, if f at x is equal to 3x plus 6, got to remember that y is equal to f at x. So I'll be able to rewrite this as y equals 3x plus 6. And, as it says in blue, y is equal to f at x. Now, second part is we're going to interchange x and y. So that means our graph is, or it's going to be written as x is equal to 3y plus 6. Now what we're going to do is we're going to solve for y again, isolate the y. I'm going to do that by, first of all, subtracting 6 from both sides. And then I can divide both sides by 3, and I'm left with y is equal to x minus 6 divided by 3. Or y equals x minus 6 divided by 3. That way. If I replace y with f inverse of x, my full answer is going to be f inverse of x is x minus 6 over 3. When I graph these two, I'm going to find my first line is y equals 3x plus 6. That's that line. The line x minus 6 divided by 3 is going to be that line. And you will see how it's a reflection over the line y equals x when I draw in that line y equals x. One of the points is 0, 6 on my original function. On my inverse function, it's going to be the point 6, 0. Negative 3 is a point that belongs to both graphs. Let's look at y is equal to x squared minus 4. That means that x is equal to y squared minus 4. It also means that x plus 4 will equal y squared. If I take the square root of both sides, I'm left with y is equal to the positive or negative square root of x plus 4. So when I graph this now, y equals x squared minus 4 is drawn. My inverse is the positive and the negative square root of x plus 4. As you can see, that's going to be my inverse graph in red. The blue line, again, is the reflection line where y is equal to x. And as you can see, if I flipped it over that line, it's going to map onto the red line. So the inverse is, again, not a function. Could you make it a function? Well, you could if you restricted your original domain to be only the part of x greater than or equal to 0, or we could have limited it to x being less than or equal to 0 as well. So your assignment is page 51, number 1B, 2B, 3A and B, 4A and B, 5A, B, C, 6 to 11, 12A, C to 15, A and C. And that's it for chapter 4.